This week, we're going to be looking a little more closely at logarithms and how they work and developing some properties for working with them. And then we'll segue that into solving equations. And pretty often, one or more of these will come up in solving an equation. So I wanted to give kind of a brief overview. We'll talk about all this more in class, of course, but um, just as a reminder, an exponential statement looks something like, just as an example, like 2 to the third equals 8, right? 2 raised to the third power, so 2 times 2 times 2, or 3 copies of 2, is equal to 8, so 2 to the third is 8. As a logarithm, that same statement, right, that same relationship can be written like this. The log base 2 of 8 is equal to 3, right? In other words, you can sort of measure split 8 up into 3 copies of the base 2. So some exponent properties that, these in theory are a review, but for dealing with powers of a like base, right? So I'm just going to pick something and kind of write these as examples because I think that looks is a little bit easier to kind of think through and keep track of rather than writing it with like a whole bunch of, general like letters and things. I'll write that down too at the end. But for products of like bases, so say we want to take like 2 to the third times 2 to the fourth. Again, the bases are the same. If the bases are the same, then really this is shorthand for 3 copies of 2, and this is shorthand for 4 copies of 2. All multiplied together because that's what exponents do. If we're multiplying those two things together, then what I could do is just count up how many 2's that we have, right? Which would be 3 plus 4 is 7. So for products of like bases, we can simplify or combine things by just adding the exponents. So 2 to the third times 2 to the fourth becomes 2 to the 3 plus 4, or 2 to the seventh. So that's sometimes called the product rule for like bases, but that's how you deal with multiplying powers of the same base together. You just add the exponents. For dividing, then kind of a similar idea. If I have, let's say 3 to the seventh divided by 3 squared, well then again, this is 1, 2, 3, 4, 5, 6, 7 copies of 3 over 1, 2 copies of 3. And since you're dividing, and the way these things are all, all these copies that I keep talking about, the way those are all combined is multiplication, we can start reducing, right? There's definitely a 3 on the top and bottom. We can reduce those. Then there's another 3 on the top and bottom. We can reduce those. And so you see what we're left with is 1, 2, 3, 4, 5 copies of 3 in the numerator. Now that's the same thing you get if you take 3 to the 7 minus 2. So in the same way that division is typically in some sense kind of the inverse or the opposite, right? Like working backwards of multiplication, we see that the way you combine the exponents is kind of the inverse or the opposite as well. So when you multiply like bases, you add the exponents. When you divide like bases, you subtract. So this is, and it's always top minus bottom, by the way, because really what's going on is this sort of cancellation thing. So if the fraction that we started with is sort of top heavy like this one is, right? The top's bigger. Oh, hey, I just noticed that I wrote 5 squared, which is not at all what I should have written. Sorry if that was confusing and you were shouting at your screen for me to change it. Yeah, that should be 3 to the fifth because 7 minus 2 is 5, but the base is still 3. So that's how quotients work. Powers, so like a power raised to a power, so say 5 squared raised to the fourth. This means 5 times 5. This means take 4 copies of those things. So 5 squared, 5 squared, 5 squared, 5 squared, 4 times. But then we're multiplying them all. So 1, 2, 3, 4, 5, 6, 7, 8. And if you count all those up, we have, I just did, you have 8 copies of 5, right, or 5 to the 8th. Now again, though, the sort of, shortcut, or like the quicker way to do that is to just multiply these. Really, you can think of this as doing this over and over again, but just like if we need to add the same thing over and over again, we multiply instead. The same thing's true here. So this becomes 5 to the 2 times 4, or 5 to the 8th. Okay, so products, right? Multiplication turns into addition. Quotients, division turns into subtraction. And powers, for those of you out there who really care about the color coding, power raised to a power turns into multiplication of the exponents, right? I didn't highlight that the same way I have been. Sorry, that would have bugged me. Okay, there you go. Now on the log side of things, something to keep in mind is that a logarithm, like when you evaluate a log, what you're finding is a power, right? 2 to the 3rd, the value of the log is 3. So you're finding the sort of missing or unknown exponent. What that means then is that if you take the log of a product of some sort, and that the base, I'm probably just not going to write the base in here, because anytime you do this, you just keep the base consistent, like you don't change it. So I'm going to write other logs down in a second. They're just going to have the same base as we started with. Say I had the log of, this will probably work a little bit better if I have things that can't be combined in like an obvious way, right? Log of 2 times x. In a sense, we're sort of reversing or working backwards from this process, right? This multiplication that's happening here, because we're taking a log, what we're really talking about are what goes on with these exponents. So this becomes the log of 2 plus the log of x. For a quotient, let's just say, I don't know, y over 3. It doesn't matter, I just need something, but I don't want to use numbers because then we would combine them. This would be the log of y minus the log of 3. So in the same way that here, when you divide, you're sort of taking some away. It's the same idea here. So the quotient rule for logarithms means that division turns into subtraction, but subtraction of 2 separate logs. That part's important. These properties are actually one of the reasons that people, 400 years ago, developed logs in the first place, to make some arithmetic stuff easier. But the product rule for logs, multiplication turns into addition, quotient rule, division turns into subtraction. And then the power rule, well, one way that we could think of this x squared is x times x, right? It's like 2 copies of it sitting there. And if it's x times x, then I could split it up as the log of x plus the log of x, right? Using the product rule. But those are the same, so typically we would just combine them and write that it's 2 copies of the log of x. This is the power rule for logs, which says that if you have a power on something inside a logarithm, you can bring it down and it basically turns into a coefficient. That's really useful in a lot of stuff, as we'll see when we get into solving equations and stuff later on. So there you go, product rule, quotient rule, power rule. Now I will just be upfront about the fact that these are like, counterintuitive. to what we're sort of used to dealing with, right? These are not properties that feel like properties of other things. Like they work for logarithms, but they don't really work for anything else. That means they're probably going to take us a little bit of time to get used to, and that's okay, but that's why we're sort of starting now. So one quick example of stuff that we can do with this. I've got the log of 3x squared times y all over 2z. This is a big jumbled mess, right? We've got all sorts of different things running around here, but I'm going to show you how we can use these log properties to turn it into something that at least doesn't look quite as intimidating, or at least looks different. So first of all, notice that there are a bunch of multiplications here. There's also this division happening of the whole thing. And then in at least one place, we've got a power on something. So what I'm going to do is start expanding this. The thing I'm going to do first is deal with that subtraction using the quotient rule from up above. So that turns into minus the log of 2z. And then I'm going to look at smaller pieces, right? So this has some multiplications. I'm going to break those up. May actually need more room. So the log of 3 plus the log of x squared plus the log of y. That's taking each of the multiplications there and there and using the product rule. Minus, that's this one, just carrying it down. And then there's also multiplication right here that I'm also going to expand using the product rule. I do want to be a little bit careful though, because I'm expanding one thing into two. That's why I've thrown this big set of parentheses here. The log of 2 plus the log of z. Oh yeah, and in case you haven't done stuff where you've had to write z's in math context before, make sure your z's don't turn into 2's. That's why I've crossed mine, but just make sure you can tell them apart. Well, and that I can tell them apart. Okay, now looking at what we have at this point, the log of 3, this is a log base 10, so the log of 3 is not anything that cleans up in any kind of nice way, so I'm just going to leave it as the log of 3 plus, now here I've got the log of x squared, which has a power inside it, so I can use the power rule to bring it down, so it becomes 2 times the log of x plus the log of y. I don't have any context for what y is, so I can't do anything to clean that up, minus the log of 2. Again, that one's not very, it's not going to simplify nicely, right? You can check in a calculator if you want. This is some messy decimal thing, so we're going to leave it like it is. And then just here, watch out to distribute that negative. So this is minus the log of z. So kind of recapping the whole thing, notice that things that were in the numerator to begin with ended up being positive in the final version of this. Things that were in the denominator ended up being negative, right? And the idea is that we're done when I've expanded everything as far as it can go, when each of these is sort of in lowest terms and doesn't simplify any further. Okay, we'll do some more in class and spend some more time with this, but now you've at least got an idea of what to expect. So thank you, and I will see you in class.